So in this session, we'll have a look at the architecture and pinout of the 80486 processor. In the previous sessions, we had a look at 80286 and then 80386. So we look at 80486. We look at what are the main differences in architectural features in terms of 80386 and 80486. 80386 is also a 32-bit processor. 80486 is also a 32-bit processor. They have a lot of common characteristics. What we will look at more is what is the difference between the 486 and the 386 architecture. So as I said, 80386 is also a 32-bit processor. You have a 32-bit data bus. This is the internal data bus of 80486. This shows the architecture of the 80486 processor. Now 80486 has the bus interface unit. The bus interface unit again fetches instructions, it fetches data from memory, it fetches data from input-output devices as well. So this is the bus interface unit. It comes with the required drivers, buffers, data bus transceivers. Now there is something new in case of 80486 which we have not seen in case of the other processors. 80486 is capable of doing what is called as a burst data transfer. So in a burst data transfer, 16 bytes of data will be transferred in a go. It's not 16 words or 16 double words. It's going to be 16 bytes of data will be transferred in a single go, or it will be done in a single burst cycle. Now these 16 bytes are transferred as 4 double words. They are done in a period of 5 clock cycles. So in a period of 5 clock cycles, 16 bytes of data will be read from memory or an input device and it can be transferred to the processor. Or similarly, 16 bytes of data as a burst can be stored in memory or it can be sent to an output device. So this is called as burst data transfer, and this completes in a period of 5 clock cycles. It doesn't require many clock cycles. In a period of 5 clock cycles, it is capable of finishing these 16 bytes of transfer. So you can see that the bus interface unit of 80486 also has what is called as the bus burst control available. Now 80486 also has a cache unit which is present within it. The cache also can do data transfer with memory. Data can be transferred from memory into the internal cache of 80486. Now what exactly is cache memory and what is the significance of having an internal cache? We will discuss that in the later sessions. But right now what you have to understand is cache is going to be an extremely fast memory, and there is up to 8 KB of internal cache present within 80486. And data transfer takes place from the normal memory into the internal cache memory, and there is a cache control unit which takes care of it. Another unique feature which is there in the bus interface unit of 80486 is that it has a parity generator and checker. The purpose of this parity generator and checker is every time data transfer takes place, it also checks whether the data transfer has been done correctly by checking the parity. We'll see more details about the pins which are associated with parity when we are going on and looking at the pinout of 80486. So what is new in the bus interface unit is going to be the fact that it supports burst data transfer, and it also supports the internal cache which is present within 80486, and it also does a parity generation and checking, something which was not there in 80386. In 80386 based general computing systems, this parity generator and checker circuitry had to be external, whereas in 80486 this parity generator and checker circuitry is going to be internal. Now there are a few more units which are present in 80486 that were not there in 80386. One of course which we have discussed is the internal caching. There is internally 8 kilobytes of cache available within 80486. Now this again was new from the 486 processor onwards. All Intel processors now have multiple caches and multiple levels of caches present within them. So about 8 kilobytes of cache is available internally in 80486. This is again different from the 386 processor. Then what else is different? There is also the floating point unit available in 80486. Now this 80386 didn't have an internal floating point unit. If floating point instructions were to be done, an external coprocessor was required. With 80386 we had used the coprocessor which was 80387 was the coprocessor which was used with 80386. So there was an external coprocessor which did the floating point operations. But in case of 80486, that coprocessor is present internally. You have a floating point unit. The floating point unit comes with its own floating point register file also. So the three new units which are present within 80486 are going to be the floating point unit. There is going to be the cache unit. There is a modified bus interface unit which can do burst data transfer, which can do cache control, which can also take care of parity generation and checking. These are the features that are new in 80486. Now, what else is there in 80486? Similar to what is there in 80386, once the instructions have been fetched, they move to the decoding unit. So there is an instruction prefetcher where there is going to be a 32-byte queue. That was also there in case of 80386. So it means 32 bytes of instructions are fetched in advance and they are going to be put into the 32-byte queue. Now these instructions are pre-decoded by the decoder unit present. The decoder unit then passes on the instruction to the control unit. Thereby it goes either to the arithmetic and logic unit or it goes to the floating point unit for execution. So there is an ALU, there is a control unit, there is a decoder, there is an instruction queue. All of that was there in case of 80386 also. Then for memory access, when we are talking about virtual memory and when we are talking about protected memory, we are talking about memory greater than 1 MB, we are going to have segmentation and paging. To support segmentation and paging, there is the segmentation unit and there is going to be the paging unit available in case of 80486. That was there in 80386 also. So how do we follow an instruction? An instruction is fetched by the bus interface unit. It is put into the instruction queue. It is decoded and then the control unit decides whether the instruction is meant for the ALU or whether it's meant for the floating point unit. If it is for the ALU, it is moved into the ALU which executes the instruction. And for protected memory, we have the segmentation unit and paging unit. And what is new in 80486 of course is the floating point unit present internally, the internal cache and the fact that it supports burst mode of data transfer, parity generation. These are the new features which are associated with 80486. There is also a version of 80486 which is 80486 SX, which doesn't have internal cache or it doesn't have the internal floating point unit. Otherwise the architecture is similar to 80486, but we are not interested in 80486 SX because this is a toned down version of 80486. We are rather interested in the architecture of the original 80486 processor. So we will concentrate on 80486. Now these are the different units within 80486. We will also have a look at the internal architecture, or we'll have a look at the pinout of the 80486 processor. So the pinout of 80486 processor, some of the pins are quite similar to 80386. There are new pins which are added because we have more complicated architecture where we have cache, we have the internal coprocessor present as well. So some new signals are going to be present in order to support these new units. Let's start with the signals that we are familiar with. There is the clock, reset and ready. Rather, this is called as the RDY signal in case of 80486. Rather than ready bar, it is RDY bar. That is the terminology used, but the purpose of this signal is same as the ready signal. Whenever the external device wants to slow down the data transfer, it makes the ready signal low, as a result of which 80486 is going to add wait states in its normal bus cycle. There is the clock signal. The usual clock frequency of 80486 is 25 MHz. There are also 33 MHz version of 80486 which is available. The reset signal is used for resetting 80486. So these are the signals which were common starting right from 8086. We have been seeing these signals. Now, other than the clock, reset and ready, we have the address and the data lines. We have the address lines A20, A2 to A31. Remember, in 80386 itself, we didn't have the address lines A0 and A1. So address lines A0 and A1 are not available in 80386. They are not available in 80486 as well. Instead of A0 and A1, if you remember, we had 4 bank enabled signals: B0, B1, B2 and B3. They are the same as in case of 80386. There is no difference there. And of course, we have the 32-bit data bus, which is going to be D0 to D31. And just like 80286 and 80386, the address and the data bus is non-multiplexed. So we have the address line separately, we have the data line separately. Now you can see there are a few more signals which I have classified under the address and the data lines. The first signal is called as bus size 8. It's a low active signal. If I connect this signal to ground or I make bus 8 0, then it means that only the data lines D0 to D7 are going to be active, meaning that I have a 8-bit data bus externally. The processor remains a 16-bit processor, but all data transfers are going to be 8-bit data transfers. There is one more line, bus size 16. We had this in 80386 also. If this signal is made low, then it means that the size of the bus would be 16 bits, D0 to D15. So you can control the size of the bus. You can make it 8 bits, 16 bits, or you can make it as 32 bits, the normal size. If both of these signals are going to be inactive, then it means it's going to be a 32-bit bus. You have one more signal here which is called as address 20 mask. Now, please note all these signals are low active signals. The address 20 mask signal, what it does is it masks the upper 12 bits of the address. Only address lines A0 to A19 will be validated. The rest of the address lines, which are going to be A20 to A31, are going to be ignored. So this makes it compatible with 8086. So if you make it compatible with 8086, or it is going to be working only in real mode whenever A20 mask signal is made 0. So the only address lines that would be considered are A0 to A19. The rest of the address signals are going to be masked or they are going to be made 0. So you're forcing 80486 to work in the real mode of operation. So these are the address and the data lines. The 3 new lines, of course, or rather the 2 new lines, because bus size 16 was available in 80386 also. The 2 new lines with respect to 80386 are bus size 8 and the A20 M bar signal, which is A20 address mask signal. So this is the address and the data lines. Let's have a look at the control bus. Same as what was there in 80386. Memory/IO bar. If this signal is high, it's going to be a memory operation. Low, it's going to be an IO operation. Read bar/write. If this signal is high, it's a write operation. If it is low, it's a read operation. D/C bar. If this signal is high, we are doing a data read or a data write. If this signal is going to be low, it means that we are doing an instruction fetch. So this is also used with respect to interrupt acknowledge. When this C bar signal is low, it also indicates it's an interrupt acknowledge bus cycle. The purpose of these three signals remains the same. In fact, the fourth signal, address strobe, which indicates that valid address is available on A2 to A31, is also similar to the address strobe signal which is available in case of 80386. So these four signals remain the same whether it is 80386 or 486. Memory/IO indicating whether it's a memory or input-output operation. Read-write indicating whether it's a read or write operation. D/C indicating whether it is a data bus cycle or it is going to be an interrupt acknowledge or code bus cycle. ADS, which indicates that valid address is available on A2 to A31. So these are going to be the control signals. Now there are a few more signals which are available, which are related to bus transfers, but they are new in case of 80486. Those are the parity signals. There is data parity 0, data parity 1, 2 and 3, and there is something which is called as a parity check signal. You can see that data parity 0, data parity 1, data parity 2 and 3 are bidirectional, whereas the parity check is going to be an output signal. Now, the parity bit is generally associated with 8 bits of data. So when you have a 32-bit bus, it is equivalent to saying you have 4 8-bit buses which are going to be available. So that is going to be how your parity is generated. A 32-bit bus is considered to be equivalent to having 4 8-bit buses. The data parity bit 0 is associated with the bus D0 to D7. Data parity 1 is associated with the bus DA to D15. Data parity 2 is associated with the bus D16 to D23. And data parity 3 is associated with the bus D24 to D31. So each of the bus 8 bits lines are connected with the parity. So D0 to D7 is associated with data parity 0. Now, what is followed by 80486 is even parity. So it ensures that there are always an even number of ones. That is what is going to be used for parity checking. So if you say that the data available on D0 to D7 happens to be 10101010, which is equivalent to AA, there are 4 ones available in it, which is going to be an even number of ones. So DP0 in this particular case will be 0. If the data available on D0 to D7 happens to be AB instead of AA, so AB would be 10101011. In this case, there are an odd number of ones. So DP0 would be 1 to maintain the even parity. So each of these parity bits are associated with 8 bits of data. So D0 to D7 with DP0. Now, these are bidirectional because you would be reading data or you would be writing data. Whenever you are writing data, parity is generated on these particular signals. So data is written into memory, then parity is generated on DP0, DP1, DP2 and DP3. When data is going to be read, the parity has to be checked. So at that point of time, DP0, DP1, DP2 and DP3 are going to be inputs. They have the parity along with the data. So during a read operation, just like your data bus is an input, DP0, DP1, DP2, DP3 are inputs. And during a write operation, just like your data bus is going to be an output, DP0 to DP3 are also going to be outputs. So they follow the direction of the data. So if data is transmitted, DP0 to DP3 is transmitted. If data is received, then DP0 to DP3 is also received. Now, whenever data is read, 80486 internally does a parity check. And if there is an error, parity check error will be raised. So PCH bar signal will go low, indicating that there is a parity error. Now there is a way by which you can disable parity. If you feel that you don't want to do a parity generation or a parity checking, you can disable the process. How do you disable the process? By consistently pulling up DP0, DP1, DP2 and DP3. If you're going to pull up all these four, then automatically the parity is going to be disabled. So that is going to be how you can disable the parity. So these are going to be the signals which are associated mainly with the bus of 80486. Let's look at the other signals. There is going to be your hold and hold acknowledge signals. Remember, hold and hold acknowledge was used with DMA process. Now in a system which has 80486, it's also possible that there are other bus masters present in the system. Now one way is for the bus masters to control is to use hold and hold acknowledge. The other way is there is a bus request and a back off signal. A bus request signal is generated by 80486. It's an information to the bus masters, and if there is an arbitrator, when there are multiple bus masters, there will be an arbitrator who says who becomes the bus master at a given point of time. So this is an information to the other bus masters and the arbitrators that 80486 is currently doing a bus cycle or it is planning to do a bus cycle further. So as long as this signal is active, no other arbitrator or bus master is allowed to take over the bus. Now if it so ends up that there are devices which are not able to take control over the bus, it is because of 80486 continuously doing an operation, the other devices are held back. This is what is called as a deadly embrace. In order to prevent that, what the other devices can do is they can give a signal which is called as back off. Back off is a low active signal. If this signal is made low, automatically 80486 will tri-state all its buses and it will stop doing the data transfer. This happens when the other devices or other bus masters have been waiting for a long time and 80486 has not surrendered the bus and has kept the B request signal active for a long period of time. So this is associated with multiple bus masters being present in the system. Now let's look at the other signals. These two signals, that is the burst ready and the burst last signal, these are going to be associated with the burst data transfer. I said that in case of burst data transfer, 16 bytes of data is going to be transferred continuously. It is done in 5 clock cycles. 16 bytes of data will be transferred. That is called as a burst transfer. Now, if a device or a memory which is indulging in burst transfer is not able to transfer data at the rate at which the processor expects it, it can make the burst ready signal low. This must be an input signal, it is not an output signal. Burst ready is going to be an input signal. So the direction of this particular signal is, it is going to be an input signal. So whenever the memory device is not able to do this burst data transfer at this 5 clock cycles which the 80486 expects, it can make the burst ready signal low, indicating that the 80486 has to introduce wait states into the burst transfer. There are two ready signals. There is one ready signal which is used for the normal data transfer. There is another ready signal which is used for the burst data transfer. So memory devices which support burst data transfer but they are not able to do it at the rate of the processor can slow down the processor by introducing wait state using the bus ready signal. Now there is one more signal which is going to be the burst last signal. This is an output signal. Whenever the signal is going to be active, it indicates that the burst data transfer is over. The end of the burst data transfer is indicated by the burst last signal. As long as this signal is going to be inactive, it essentially means that a burst data transfer is happening. Now there are going to be, of course, the interrupt signals. There is the NMI and the INTR signals, the non-maskable interrupt and the maskable interrupt that was legacy from 8086. We have had it in 8086, 286, 386 and 486. They remain the same. There are two new signals which are associated with the flash, which is with the cache memory. So there is going to be the cache enable. The KEN signal is cache enable signal. When this signal is made low, the internal 8 KB cache is activated. If this signal is made high, the internal 8 KB cache is going to be disabled. So it's used for enabling the internal cache. There is a flush signal which is used for clearing the internal cache completely. So if you want to have the contents of the internal cache completely cleared, the flush signal is made low. When it is made low, the internal cache contents are going to be completely cleared. Then there are two signals which are associated with the internal floating point processor. Whenever the floating point processor which is present internally there is a floating point unit in 80486. So whenever there is an error in the internal floating point unit, a floating point error is activated. Now it is also possible that the external device might ask the processor to ignore this floating point error. So there is a signal which is called as ignore error. So this is used for ignoring the floating point error. This is an input, and this signal is an output signal, that is floating point error, which is raised whenever there is an error in the floating point unit. There are two more signals which are actually associated with the cache. One is the A-hole signal, the other is the external address strobe signal. Now this A-hole signal is going to be used, it's an input signal. Whenever this signal is going to be active, it means that there is going to be a cache invalidate cycle which is going to take place internally. But this cache invalidate cycle is not done by 80486, but it is going to be done by an external device. An external device is going to invalidate the contents of the cache. Now what is going to be the address that is going to be invalidated will be given on the address lines. At the same time, the external address strobe signal will be made active, indicating that an external device is giving the address so that it can validate the invalidate the internal contents of the 80486 cache. Now these signals are more sensible in a multiprocessing environment. We would not be looking at this in much detail. The actual working of these two signals is way beyond the scope of this course, but that is the function of these two signals. They are used during a cache invalidate cycle. If the cache invalidate cycle is not done by 80486, but it is rather done by an external processor, then these two signals are going to be used. There is going to be, along with the lock signal, one more lock signal which is available, which is P-lock. Lock was an input which we saw in case of 80386 also. So this lock signal essentially is generated by, it's not an input signal, rather it is going to be lock bar, which is going to be an output signal, and P-lock, which is going to be an output signal. The lock signal is used for indicating that 80486 needs the bus and no other device must take control of the bus. That is the function of the lock signal, which we saw in 80386 also. Then there is a P-lock signal which is called as a pseudo lock signal. This time the bus cannot be taken over by any other bus master, but the reason is, it is because the floating point unit within 80486 wants data. It is not because of the processor wanting data, it's because of the floating point unit within 80486 wanting data that no other device must take over the bus. So lock and P-lock have the same purpose. The only difference is lock is raised for internal purposes of the other units within 80486, and P-lock is going to be raised for the floating point unit which is present within 80486. Now there are two more signals available which are going to be the PCD and the PWD signal, paging cache disable and the paging write through signal. Now this we will see whenever we are talking about paging caches. There will be a session on paging cache. Then we will have a look at the PCD and PWT. The PCD and PWT signals actually reflect the contents of an internal register. So when we come to the cache, we will then have a look at PCD and the PWT signal. Then we will see what is the function of that register and what does these signals have to do with it. So this is going to be the architecture of 80486 and the pinout of 80486. The main difference between 80486 and 80386, both of them being 32-bit processors, that in case of 80486, there is going to be an internal floating point unit. There is going to be an internal cache which is going to be of 8 KB size, and that 80486 is also going to support burst modes of data transfer, where you can transfer 16 bytes in a matter of 5 clock cycles. Otherwise, the architecture of 80386 and 486 remain almost the same. So I'll stop with this in this session.